All right, good afternoon, everybody. Welcome to today's session, Networking Optimizations for Multi-Node Deep Learning on Kubernetes. Before we get going, I'd like to remind everybody to please rate the session afterwards on the Schedule app. Also, if you have any translation needs, we got translation going on over here. Just punch in that URL, type in the code, and then you have the app on your phone. Please use headphones, though, versus the audio speaker. I'd like to introduce the speakers for today. Erez Cohen, Vice President for CloudX and AI Program at Mellanox, and Rajat Chopra, Principal Software Engineer with NVIDIA, working on AI Deep Learning infrastructure. With that, I'd like to hand it back over to you guys. Thank you.
Thank you very much. So good afternoon, everybody. We thought to start with why machine learning, but to be honest, these days it's quite obvious. Machine learning is everywhere. Even we have this little thing here that translates, it is all machine learning based. So really machine learning is everywhere, and we definitely want to run machine learning in Kubernetes as well. This is just a basic definition of what machine learning is from Wikipedia. In essence, it's just the ability to allow machines to learn from data and program themselves. But the real development over the past few years is around a subfield of machine learning called deep learning or deep neural network, which is basically an implementation of machine learning which is inspired by the brain. In other words, taking a biological implementation, if you like, and translate that into software implementation. This is the very basic of neural networks. We'll not do a neural networks course here, but I do want you to understand the basics so it will help us understand the challenges in running in large scale. What you see here is a single neuron which has three inputs on the left-hand side, x0, x1, and x2. And with each input, we associate a weight, w0, w1, and w2. And those weights are very important. Those weights will define if this neural network will work properly or not. So we need to tune them, and we'll talk about how we do that in a minute. Those inputs and the weights are going into the cell body. There's a simple function there that decide if this neuron should fire or not. So as a single neuron, that's pretty simple. And a single neuron doesn't really help us a lot. But when we combine them together, interesting things start to happen. This is a neural network that do image processing and predict if an image is a digit, 0, 1, 2, all the way to 9. You can see the output on the right-hand side, and the input on the left-hand side is an image. This is a three-layer network, and as you can see, there's many connections between the neurons. The neurons are all connected, interconnected to each other. Now, on every connection, there are weights, as we said earlier. So you can assume that there's quite a lot of weights on this neural network. But neural network can be much bigger. This is a 12-layer neural network, and as you can imagine, there are much more parameters, much more weights that needs to be tuned for this neural network to work efficiently. And this is definitely not the biggest neural network. Actually, today we're seeing neural networks that are multiple hundreds of layers, and they can be very, very, very large and very complex. Now, when we build a neural network, in the beginning, it doesn't act as we want it to be. We need to train it. We need to teach it. And the way we're teaching neural network is through a process where we feed information that is pre-classified or pre-tagged. A good example, a very classical example, is an image processing when we are trying to teach a system to distinguish between dogs and cats. So we will feed images of dogs and cats, but we know that there are dogs and cats. And on the output, we will check what was the result, and we will try to feed back and fix those weights that I said earlier through some kind of algorithm, until the point where we feed a dog image and it will say it's a dog in good probability, and a cat image and it will say it's a cat. And then at that point we say that the neural network is trained. And then we can move to the inference phase. The inference phase is basically the execution part. This is where we actually push an untagged data. It can be an image that we don't know exactly what it has, and it will tell us if it is a dog or a cat. Of course, this is a simplified example. The training phase is very challenging. It is very, very much compute-intensive process. This is why NVIDIA GPU is such a wonderful solution, because it allows us to drive computational very fast. But what we see is that those neural networks are growing in complexity, and the input data is growing as well. And actually today, if we are looking at modern models and problems, it takes us weeks to train a model. Obviously, that is very challenging. It's challenging because a week is a long time, but also we need to train quite often. There's two reasons why we will need to train often. One is because developing a model is not a linear process like writing a C code or any other language you're used to. You write the model, you train it, you see how it behaves, you change it, and then you train it again, and you go on and on. Now, if you do that and it takes you a week between training, that's very inefficient. Another reason is that just like in life, you have to keep on learning. You build a model, you train it, great, you put it in production, but things change. The world is dynamic, and we need to be able to keep on teaching the model to and bring it to be more accurate. So what we really need is we need to accelerate our training time, and the only way to do that is to do scale-out computing, basically add more computers. So how do we do scale-out in machine learning? This paradigm called data parallelism. And basically what it does is basically instead of having a single computer that has all the input data, we just add more computer, we scale out. And we take the input data, we split it in between the different computers. So in this example, each compute will get 1/6 of the data. And then it do a local training. Now, if each of the computes will do local training, you'll end up with 6 different models, because each of them was working on different data elements. So that will not work. What we really need to do is we need to combine those machines' power together. And the way to do that is basically split the data into mini batches, let's say 32 images, do local training on each node, and then communicate the results and combine them together through the network. It can be to a single computer, it can be between the computers, there's different ways to do that. And eventually, this process, when we are iterating this multiple times, it can be hundreds of thousands or even millions of iterations, we will get a single model that is trained. Now, when we look at those network elements in the training phase, we see that the communication pattern is very, very challenging. It will be usually very high performant, high throughput. Those models can be transferring tens and hundreds of gigabits per second. So it's a lot of data from every computer, and you have a lot of computers usually doing that. It will be very high message rate and low latency requirements. And it has collective operation in nature. What I mean by collective operation is that all those nodes are working together. They work on a mini batch, they communicate, and they are waiting for each other. So they work as a collective. And as a collective, you need to wait for everybody and synchronize everybody together. And this type of communication pattern very much reminds us of high-performance computing network, which are all the supercomputers. And we know from a lot of years of experience that advanced network techniques such as RDMA and GPUDirect are critical for having an efficient training. I mentioned RDMA. Let me just give you a quick explanation about what is RDMA. RDMA is a remote direct memory access. It is a transport service. You guys probably know TCP and UDP, so it's in the same layer more or less. And, but it was designed much later, and it is much more advanced in terms of feature set. It provides us ability to do read and write over the network, not only send, receive. And it provides us ability to do kernel bypass. Kernel bypass is when the application talks directly to the hardware, bypassing the kernel, and by that we get very low latency. And it provides full hardware offload, at least with the Mellanox NICs, which means that we can transfer hundreds of gigabits without any CPU intervention. So the CPU load is 0, and the efficiency is very, very high. RDMA started from a technology called InfiniBand, but today it's part of Ethernet. It is called RoCE. And the interface, the software interface, is not sockets. It is an interface called verbs, which is very important because the normal net devices that we transfer to the container doesn't provide RoCE or RDMA interface. We need a different interface. GPUDirect is a technology that allows us a better efficiency of sending and receiving data from the GPU to the network. What you see on the top right-hand side is how do you get data in and out of the GPU memory without GPUDirect. So what you would do is typically copy data from the GPU memory to the host memory, copy the host memory to a buffer in the host memory again for the network, and send it out. That's not very efficient, obviously. GPUDirect is a technology that developed by NVIDIA and Mellanox together about 10 years ago, which allowed the NIC and the GPU to communicate directly to each other. So the NIC can access the GPU memory and send and receive data directly from there. Obviously, it provides a much more or much better efficiency. So how do we enable RDMA and GPUDirect in Kubernetes? So today, we are using SRIOV as a mechanism to expose RDMA and GPUDirect. SRIOV is a PCI specification, stands for single root I/O virtualization. And basically, what does it mean? It means that you can take a PCI device, slice it, and provide slices to an application. It's called virtual function. What you see on the images on the bottom here, on the left-hand side, you see the standard configuration. On the right-hand side, you see the SRIOV, and you can see that every virtual function coming from the device has a net device, but also the RDMA device, those devices that are needed for RDMA, that can be mapped into the container. There are CNIs and device plugins to provision SRIOV. It is completely standard and upstream, and you can find the links in this page. So from a container perspective, the container will see when the SRIOV device and a CNI plugin are activated, the container will see both an RDMA device, this is the IBDev that you see here, as well as a net device under the namespace of that container, and will get a slice of the NIC as part of the SRIOV interface. So how does it look from an orchestration perspective on the Kubernetes level? So first, the SRIOV network device plugin will advertise the SRIOV's capabilities, so basically how many virtual functions each device has. And then when you launch a pod, it will define that it needs SRIOV, in case that it needs SRIOV, so it will say I need a virtual function. The Kubernetes scheduler then will run the pod in the right host with those resources. The device plugin will allocate the virtual function that will be connected to that pod. The allocated device is communicated with the SRIOV CNI because we need the net device to run on that interface, and then the SRIOV CNI will move the virtual function net device to the pod namespace. In Kubernetes today, you're not allowed to run more than one interface or one CNI into a pod. And for that, Multus or similar plugins were developed. Multus is a meta plugin which allows to provide multiple interfaces to a pod. There will be always one interface which will be the prime, the master interface. This is the standard kind of ETH0 that you're using, and this is where all the security groups and policies and so on will be applied. But then Multus provides you the ability to connect additional CNIs, one or more. It can be more than one. In our case, it is obviously SRIOV. And those interfaces, although they are providing connectivity, they don't have any security policies around them, and they are not able to be present under the Kubernetes interface. And with that, I will hand to Rajat.
Hello. Welcome to part 2 of the post-lunch session of the last day of the conference. I'm sure you guys are excited. Try to make it interesting. Funny thing I noticed that when Erez said RDMA, the AI thing running over there was saying RDNA. It's, I was noticing, and it's more clever than I was afraid of. Anyway, we'll get to,
Probably my accent.
Or I'm smarter than it, or whatever. All right, so Erez talked about all the ingredients that you would need to get deep learning going on Kubernetes for multiple nodes. You need RDMA and everything. He put it on the list of all the ingredients. Now, if you put all these ingredients together, you will have a large data center. Hopefully, if you want to scale out much further and further, you would have a large data center and you would be able to put these pieces together and things would start to work. I'm afraid not. You will run into issues, and those are the issues which I'm going to list down. If you're ever going to try this in your data center, you're going to bring this infrastructure up, you're going to have to take care of these issues in mind. Some of them are functional issues. You will see that stuff is not working. And some of them are performance issues. You will see that stuff is working at as low as 1% of the performance that you thought, or as I would have shown in the slides. So I will go through some of this list, and we'll probably start making some counts of things that I'm going to list. And in the end, I'm going to show some performance graphs on how, when we put in these optimizations, what do we see? Do we see the expected results or not? All right, so we'll start with priority flow control, explicit congestion notification stuff. You can read up on Google what it is. It's broadly about saying when the network is going to be shared, it's an RDMA over converged Ethernet. You're going to have trouble with other things. So, well, let's separate priority flow control things, and then let's make a separate channel. You need to configure that on the host. The ECN bits, which is congestion notification, which is just saying if there is congestion, please back off, don't send traffic, let's don't make it worse kind of things. These are things which you have to fix on your switch or the router. And then other things, you need to get this ACS thing set up on BIOS. If you don't do that, you'll see performance suffering. And then there's a GPUDirect, which it has introduced. If you don't put this kernel module in, imagine now you have 20 boxes in your data center or 200 boxes, and you didn't put one of the kernel modules thing going on in one of the boxes, just missed one. What is the beauty or the single most important principle of high performance computing? The slowest guy is going to guide the performance of the entire flock. And you say, oh, the whole thing is running on 20% performance. What's going wrong? Well, please go through the checklist. We've suffered this, so believe us. The final part is blue frame registers. If you're using Mellanox cards, if you have smaller packets, 64 bytes or less or something, and you probably want to tune this further. You don't want to see 5% drop. And it's not that 5% drop in performance is important. I translate that to 5% of your money going waste when you have invested millions of dollars in that infrastructure going. How many of these are there? 4 of these, all right? We keep going. You don't believe me probably, and these are the graphs that we measured. We didn't do PFC and ECN. The one on the left is showing 4 interface cards, the red, orange, green, and blue, trying to operate over some period of time, which is the x-axis, and the y-axis is the gigabits per second, and the max you could have gotten is 100 gigs per second. That's the card throughput. And you would see that you don't get the things right. One of the cards is just working at 20%, 20 gigabits per second. We just enable that, and you see the graph on the right, and you say nearly everyone is working together like brothers should be, and you get above 90%. But, and you can see, as anyone can, that there's some small spikes that come down and everything. We were at the 4 counts of things that we had optimized. I'm going to go next on how to remove these spikes also. If there's one single important thing that you're here for and you want to learn on how to get deep learning infrastructure on scale with Kubernetes and everything, this is the one thing which will improve your performance multifold, make it scalable, make it reliable. The problem statement is that I got these boxes, you know, the GPU boxes. Each box has 8 GPUs or 16 GPUs or 4 GPUs or whatever your favorite configuration worked. And let's connect them to the network. And the network has these top of rack switches or something. How do you connect them? If you're anyone like me or something stupid or learning, this is what I did. I put these boxes, and then the rack got over, I put these into the switch, and then get to the other rack, put these boxes, put it on the top of the rack, and then connect the part of the rack to the fabs and spines or whatever it is. Does not work. And it would work for any other thing that you would try to do. It would not work for deep learning. Why? Because deep learning has a peculiar thing. When you try to share those mini batches with your parameter servers and everything, what's going on is that the if you see this diagram on the right, top right, the information sharing happens through a ring or a parameter server or a tree or something. Whatever information goes through NIC 1 comes out of NIC 1, covering all the GPUs, connecting all the parameters that each of those GPUs communicated, goes to the other GPU node and communicates with NIC 1 also, and goes to the third node and communicates with NIC 1 again. All the NIC 1s want to talk to each other. All the NIC 2s want to talk to each other. All the NIC 3s want to talk to each other. Never would you have a situation in deep learning in the frameworks that NIC 1 is trying to talk to NIC 2. No, NIC 1 talks to NIC 1, NIC 2 to NIC 2, 3 to 3, 4 to 4. So a minor point, but a very clever point. I'm saying the single most important thing if you have to learn. So wake up, listen to this. When you wire up your servers, get your NIC 1 to switch 1, all the NIC 2s to switch 2, all the NIC 3s to switch 3, even if they're from the same box. Just a simple measure. And the result is that when all NIC 1s perform their communication pattern, they will have no extra hop, one hop, right? They all go to the same switch, they get back to the thing, there is no extra hop required. Now, extra hop is bad when you're talking about RDMA over Ethernet. That's a simple principle, very easy to understand, just that I struggle so much with putting all of these into single switch and everything. And the one important thing that you can learn from here is that if you get the number of ports on your switch is more, then the more you can scale on your cluster. If you have a 128-bit, 128 port switch, you'll be able to connect 128 machines on one switch. That would nearly mean 1,000 GPUs. 5 points did I make? This is the single most important one. Sixth point, if you don't enable this, this is going to be dysfunctional. This is source-based routing. Now, Erez introduced that using Multus, we will have multiple interfaces into the pod. When you have multiple interfaces, all of them are on a different network, and possibly would be. Do you know how routing works then? If I want to go from a box to some IP address, my destination routing table says, oh, you want to get to that subnet? Use this NIC. I say, hold on, I'm deep learning. Okay, I know which NIC to use. Don't tell me to use that NIC. I know which NIC to use. I want to connect NIC 1 to NIC 1. Don't tell me that your routing table is saying to use NIC 4 for that subnet. Well, you need source-based routing here so that when your deep learning framework is trying to share parameters, it consults the source-based routing and says, NIC 1 will always go from NIC 1. You choose the source interface and you choose the destination interface, and you need this plugin to make this working. So we all put this together. If you have a quick question I can answer now, we can take this later.
Why can't we just make it layer 2 network, VLANs?
Yeah, layer 2 network, clearly. And you would not have VLANs then, and you would not have ever the possibility of going and expanding your network when you have a 648 port switch and you say, can we have layer 3? If you don't want layer 3, yes. If you stick in layer 2, you don't need this. But you want to scale out, and we wanted to scale out. So we said, well, let's make it generic. Good question, thank you. This is roughly the final thing that I'm going to talk about. We can spend a lot of time on this, and if you want, we can close this sooner, but these are real performance measurements. Now, I could have gone on to hundreds of GPUs, but I wanted to restrict and see that just 5 boxes put together, just 40 to 48 GPUs put together on different scale. What are the numbers that I got on ResNet 50, which has 23 million parameters to be shared on every one of the 50 layers when you do deep learning training on 14 million images. The y-axis is number of images per second. The x-axis is number of GPUs that I used. And the 3 graphs are on batch sizes. You can see clearly, in SGD we trust. SGD is the algorithm that we use, stochastic gradient descent, to share those parameters, and that's why you would see why the batch sizes are important, why your accuracy is important, why the training image, the speed of training is important, and how these things play. But we're the network guys. We want to make sure that, what did I do all this for? And you can see in the third graph, just in 5 boxes put together, you can see if you did not put your network right, the red line is the RDMA highly optimized stuff, and the blue line is also 100 gigs. I'm not comparing wrong NICs with stuff. The blue line was also the 100 gig NICs. And you see 2x drop in performance. That's half your money wasted. in just 5 boxes put together, 5 as in, 6 boxes put together, yeah. So 48 GPUs, you would see 2x performance loss. Now as you start to scale into hundreds and thousands of GPUs, you can calculate what's going to go happen. The top left graph is the bigger batch size, and there are 3 lines there. One is the orange line, which is the ideal theoretical maximum that you could ever get, which is what I did with 1 GPU I took, and I said, what if I put 48 GPUs? I just took that number and multiplied by 48. That's the ideal you could get. And if you see in most of these graphs, until 8 GPUs, you roughly get similar scale, and after 8, you start to peter off a little bit, the scale, the slope is not 1 anymore or something. It's because one box had 8 GPUs. It's only when the second box comes in, you use the actual network, you use the PFCs, you use the ECNs, you use the optimizations that I've been talking about. Who likes to see half of their data or half of their money going waste? Nobody. We're talking millions of dollars here, and I'll prove my point in the end with a joke. That's summary and conclusion. I don't want to stretch it. We can talk about this later, and these graphs are important. These are real measurements, and they're not done yet. We're going to improve this further. We're going to pull these red guys a little up and then try to see how they scale and everything. So I'm putting together a lab with 800 GPUs and then 1,000 GPUs, and we'll see how far it goes. And then you've seen the ML perf numbers and everything. We want to train the Resonant 50 or the more complex models, the 150 and 153 and whatnot, not in weeks as it used to take, not in days, not in hours. These results are the whole model trained in 5 minutes. So you can train, retrain, things like those. Well, this is the summary, and it's coming to a close. Finally, the upshot of the matter is multi-rail RDMA and Kubernetes is possible, and it scales very well, as we've shown. We've shown the performance numbers. There are a lot of things to take care of, and you can go through the slides. We'll publish, of course. Further work would be storage. You got a plan for it? We'll talk about it. Ambient temperature is an important thing. If you have 100 degree going on outside, you will see that performance of your data center is suffering, and you will say, what, I did everything right. What's wrong? Well, it's just hot outside. Raise your ambient pressure. There are other things. What are the clearest, biggest principles? Lowest link will guide the performance of the entire job, because it's an HPC thing. And to close, does anyone know what principle does a plane fly? This was asked to me when I was doing my pilot training several years ago, and I took the first ground instruction, and the instructor said, so you learned a little bit about how planes fly, how do they fly? And I was naive. I said, like how networks work on bits and switching and everything. I said, oh, the Bernoulli's principle or thing. No. The only principle is you put money, it flies. This is networking. Put money, it goes. Just take care of a few things. Thank you.
So if any of you have questions, we have a few more minutes, and you're more than welcome to contact Rajat or myself. I think there's a question over there.
Yes.
Do you have performance numbers vis-a-vis the bare metal versus Kubernetes that you could illustrate on?
This is Kubernetes on bare metal.
Okay. So if you remove the infrastructure and just run it purely on bare metal, how would this look like? That's what I was trying to figure out.
Exactly the same. If it's an argument that your namespaces introduce anything, they're not in the data path.
Okay.
The SRIOV, the whole idea is that there is no bridge, there is nothing. The SRIOV idea is that you take the physical interface, nearly the physical interface, make the virtual function out of it, and pull it right into it. And as Erez said, it doesn't work on those sockets, it works on the verbs. So the data plane is not even there. It doesn't even know what namespace and everything is. It does, but it's not in the path.
Okay.
Yeah, I would maybe just add one thing that we didn't talk about here, but the next phase that we will do is actually enable all the SDN controllers with the bypass. So we, in the very near future, we'll be able to run all those goodies with a full SDN and without any performance impact. That's the next phase. Any additional questions? Yeah, over here.
Can you take the mic, please? Microphone.
If we are slicing the GPU to vGPUs, right, will we see any issues here like our on
You
all
mean
these
multiple
performance.
jobs will run? Do you know
Yeah,
that's the
in
inverse of the problem we're trying to solve? We're taking one job and we're going to take thousands of GPUs. And you're saying that we take one GPU and split it into multiple jobs. So we can't compare this. I mean, I know that this is the thing that we need to work. I mean, this is a problem case, but this is not that problem statement. This problem statement is, I got a model. It takes hours to run and optimize. How can I bring it down to minutes?
Okay.
So this is not GPU sharing. This is taking everything in your data center, run one job, finish it in minutes, come back with the new parameters. There's gentleman having a question. Yes.
So if you have a large GPU cluster in which you're running different trainings in parallel, like different sets of, distributed trainings, when you keep running workload, your cluster gets somehow fragmented, like you cannot do perfect placement and you cannot put the jobs next to each other.
That's right.
So when you're using RoCE instead of InfiniBand, how much noise can it survive? Or, to make hotspots in the network? Because with InfiniBand, you somehow always like a double path you guarantee somehow the nodes will reach each other within a certain latency and with a certain bandwidth and without noise, but with RoCE is not the case.
If your question is, if I could get it right, is that with RoCE, you're sharing the network in some way. And with InfiniBand, you get the clear channel and everything and stuff. So this work is showing RoCE, but it's not occluding RoCE first, occluding InfiniBand first of all. So the principle should apply, and then we should work on IB as well. But coming back to your question, yes, if you clog your network, you will get clogged results. If you clear your network, you will get clear results. There's nothing else. But you don't forget the PFC ECN bits, right? And if you have ECN on, you would have a normally functioning cluster. But if you still are overloaded, at least you would not die with thrashing.
I will just maybe quickly add on that. In general, when you're running multi-applications in a cloud, which is high performance, you need to do placement in a network-aware manner. If you place your workloads without any network awareness, you may have challenges. And it is not available yet today as part of Kubernetes, but this is something that HPC guys are definitely doing.
But you can do network placement, but it will get fragmented eventually because you take 4 nodes and use for a job.
That's
and
right.
then those nodes get free. And then you only need 2, and then 2 are isolated, and you may not have 4 next to each other, right?
You're right. I mean, this is a problem that we faced in our data center, and we are doing a new scheduler. We have built a new scheduler for the deep learning jobs for Kubernetes, and to begin with, for these large jobs, we do gang scheduling, so that we know that the gang scheduler will put all these jobs on the nodes that are allocated. So we demarcate these nodes, saying this is a node which will run jobs which want 8 GPUs. This is a node which will run, for jobs which want 4 GPUs, which means 2 jobs can fit if you had 8 GPUs. If you have 4 jobs, can fit if you had 16 GPUs on that box. And this is a box, a separate box, labeled separately. The scheduler knows, the node selector knows, and everything, which is going to run only jobs which want 1 GPU, which means we can fit 16 jobs if there are 16 GPUs, or 8 jobs if there are 16. But that's how we try to avoid that fragmentation. It's an integer programming problem if you say I want to solve everything and not have fragmentation. Yes, it's a real problem. You will have a lot of efficiency issues, utilization issues.
I think we're maybe...
I think we're at the top of the hour at this point. So,
all right.
Okay,
if you have any other questions, I'd catch up with the guys afterwards outside. And thank you for coming to the session. Thank you.
Thank you.
Thank you.